Okay, welcome back. We were working on 16. You can do this with a partner. And then let's have a couple people who think they may have it come to the board. Pause the video, do that work, have someone come to the board to show the solution, and then we'll look back and check to see how it compares with this. Okay, so I assume you've paused the video, you've had the chat, we've looked at the board together as a class, and here's the solution. First thing to notice is they ask for magnitude. You might think that that means you can ignore all of the directions throughout the entire problem, but that's not true. You can only ignore the direction at the end once you've considered it carefully throughout the process. Now you have to choose which way the ball is going when you're working out the answer. And then at the end, you get rid of the directions that you assumed, and so that's why it doesn't matter which assumption you make at the beginning. So this will be clearer once we see how it works. What I'm going to do is assume that the ball is going to the right and then it bounces back to the left. You could assume that it's going left and bounces back to the right, and you'll get the same answer. So here's my assumption, here's my picture. The ball initially is traveling at 5 meters per second to the right, so it's positive. And then the ball bounces back with a final velocity that's going to be negative. Now the negative velocity here is 90% of 5. And that comes out to a negative 4.5, negative again because it's leftward moving at the end. So we use the equation. Oh, first we have to convert grams to kilograms. You have to multiply by 1, and a kilo is equal to 10 to the 3, so this fraction here does equal 1. And now I use the equation once I've got my mass, plug in the value of mass here. The final velocity is negative 4.5. The initial is positive 5. And this is my answer, except they ask for the magnitude, so I get rid of the sign. Now, if you had done the problem where you assume the ball was going left at 5 and bounces back to the right at 4.5, then all that would be different is this would be positive, so you'd have positive 4.5 minus a negative 5.0. And you would get the exact same magnitude, but your direction would be just positive already. So it doesn't matter which assumption you make about the ball's initial direction. Any assumption is valid since you only give the magnitude of the final answer. We're now going to learn about impulse. When forces act on objects, they deliver what we call an impulse. Impulse is defined as the force times the time over which the force acts, and J stands for impulse. So let's define these three things. F is the force that's acting on some object. T, delta T, is how long the force is pushing on that object. J is the impulse delivered to the object. That's the language we use. What's the unit for time? Seconds. What's the unit for force? Newtons. So what will be the unit for J? You've got newtons that'll be plugged in here, seconds that'll be plugged in here, so it'll be Newton times a second, or a Newton second. We can only have positive delta T. Force is a vector, so it could be positive or negative, and therefore J will also be a vector that could be positive or negative. Now we will be dealing with net impulse, and this is just the impulse delivered by the net force. So take a moment to solve number 17, and then once you've solved, you can check with your neighbor and then come and check the video for the solution. So here's the solution to 17. You use the equation above, plug in the values. Whoops, this should be newtons, not seconds here. And you get 1,000 Newton seconds. It's not newtons per second. A Newton per second would be N divided by S, and that's not what we have because we're multiplying force and time, not dividing it. So take a moment then, talk to your neighbor about number 18 once they're there, and after you all have had a chance to talk, write down your answer, and then you can come back to the video for the solution. Okay, so I assume we've had a chance to talk, and here's the solution. you want to use the equation for net impulse. Now, in this equation, if J net is fixed, then how are F net and delta t related? The answer is that they would be inversely proportional. So the change that one experiences is going to be opposite the change of the other. If you increase one, the other will decrease. Here's another way to see that. The same J net could be produced using a huge net force and a small delta t, or you could get the same J net using a small net force and a huge delta t. As long as you're multiplying a small number by a big number, and it doesn't matter which one is small and which one is big, then you get the same J net. Now, the red car and blue car experience the same net impulse, but the red car feels a lower net force. So which scenario are we looking at for the red car? How is this possible? If the red car has a lower net force, then that means the red car's crash would have to take a longer amount of time. Or in other words, it takes more time for the red car to come to rest and complete its crash. We're going to look at this again because this has had a major impact. This principle has had a major impact on how cars are built. Impulse momentum theorem. There's a relationship between impulse and momentum. When you apply or deliver a net impulse to an object, the object's momentum will change. And in fact, the two are equal. They're equal. On the left side, we could plug in the equation for delta p. So we substitute in m times the change in velocity, vf minus vi. And on the right side, we could plug in the formula for net impulse. Now, this equation says that delta p equals net impulse, which means the unit of delta p must be equal to the unit of net impulse. Is that true? Does a kilogram meter per second equal a Newton second? Let's look and see. Think about what a Newton equals. Newton is the unit of force. Net force equals mass times acceleration, ma. So what's a Newton equal to? Mass times acceleration. Mass is kilograms, acceleration is meters per second squared. So you can substitute in for a Newton with kilogram meter per second squared. Mass times acceleration. And look at that. One of the squared seconds in the denominator cancels out with that second, and now the left and right side are equal. So in fact, the Newton second is another valid unit for p and delta p. And likewise, the kilogram meter per second is a perfectly valid unit for net impulse. So whenever you use one, you could also be using the other if you prefer. I typically will use the Newton second because it's shorter. Okay, now we're going to skip down to this bullet. Net force, delta p, and net impulse, those three things will always have, what's going to be the same for those three things? The answer is not units, because net force has a different unit from either of these two. In fact, what's the same is their direction. They'll always have the same direction. Now I want to look at number 19 together. We have three equations at our disposal. The net impulse equation, delta p equation, and the net impulse momentum theorem. The equation here is so important we call it a theorem. So we've got a 45,000 kilogram truck traveling at 32 meters per second north. It hits a wall and comes to rest over 0.15 seconds. Part A, determine the change in momentum. Well, we're going to use this formula. We don't know the net impulse, we don't know the force, we do know the time. So we could use time, but we don't know force to find impulse. And so we can't find the momentum change that way. So instead, we use this formula. Now, we know mass, we know the final velocity, right? It comes to rest. So what's the final velocity? 0. The initial is positive 32 because it's going north. So you plug in and you solve. Now I happen to use kilogram meter per second for the unit. You could also use Newton seconds. That's part A. Part B, determine the net impulse. This is really easy. As soon as you know the the momentum change, you also know the net impulse. They're equal. So it's the same answer. And I switched units, but you don't have to. Part C, find the net force experienced by the truck. We know net impulse, we know time, 0.15 seconds, so we can find net force. You plug in and you solve. So give 20 and 21 a shot. Pause the video and then we'll give you the solution once you've had a chance to do it on your own. Okay, I'm just going to give you the answers. Here they are for 20. You divide by 0.85 this time instead of dividing by the other value in number 19. So it was a smaller time in 19, a bigger time in 20. And it's positive now because this time we were subtracting the initial velocity, which was negative. When we subtract VI, the VI is negative, so we're subtracting a negative or adding 32 to the equation. That's why the value came out positive for delta P and J net. Number 21, chat about this with your neighbor. What was the difference between the two trucks that we looked at in 19 and 20? Well, this comes back to what we saw before. When you have a big net force, the time of the collision will be small. When the collision or the crash takes a long amount of time to come to rest, the net force will be smaller. One can be big, the other can be small, because they're inversely proportional, and J net is fixed in the scenario that we've been given. This principle has had a huge impact on car manufacturing. Originally, cars were made to be rigid. They didn't bend or crumple. They remained intact when they collided because you didn't want to go out and buy another car, right? So imagine your car comes, it hits a wall, and you crash. The car is really rigid, so what happens? Well, in fact, the car might kind of bounce back a little bit. It stops and bounces back just slightly. This bouncing occurs so quickly, just like bouncing a ball off the ground. So imagine you hit a stopwatch, you hit a timer when the ball first strikes the wall. How long does it take for the car to stop before bouncing back off? Really small amount of time. The timer shows 0.05 seconds when you stop it, when the car has come to rest. So nowadays what we do instead is we make cars so that they have these areas that crumple. They bend, they collapse, they crunch, and they crumple in on themselves. Now that crumpling is a slower process. It takes time to crumple a car. So I've exaggerated the effect of the crumple zone by making a really, really long front end here. The cars don't really have ends that long, but the principle is kind of the same. So you hit a wall, and what happens? You hit the timer, you start the timer, but you don't stop until you've done all this crumpling and crunching and bending. So how long does it take to stop? 0.75 seconds, much longer. And that's what the crumple zone is there for. It's there to extend how long it takes to come to rest, extend the time of that collision. Why do we do it? Well, the impulse momentum theorem says this. We isolate F net, and what do we get? That if you have a bigger time, then the denominator is bigger and the net force is smaller. That's important because net force is what does damage. That's what hurts you. So a smaller net force means you'll be safer during the collision. So now take a moment, pause the video, and try to fill in these blanks and then do this last part here. Okay, the answer to the blanks, here they are. Pause the video if you haven't tried it on your own. The answers are time, net impulse, and net force. The relationship here is F net against delta T, which is inverse. Homework is up on Schoology.